Today's section is 3.4, concavity and the second derivative test. So this idea of concavity is looking at the graph, and if you have a graph like this one, then no matter where you would draw the, like look at a certain point and you would try to draw the tangent line is outside, or it's underneath the curve, no matter where you would draw it. And if that's true, then this is concave up. And for this graph right here, you have a curve like this. And I have a different way to explain it in just a second than these tangent lines. No matter which way you would draw the tangent line here, for whatever point you're talking about, it'd be above the curve like this. And this graph is concave down. So that's one idea. You could think about how you would draw tangent lines, because you want to draw the tangent line so that it doesn't intersect the curve. So for this point here, you would draw it here because it's going to keep going and never touch our curve, only the one time. You couldn't draw it in here because it would intersect the curve, so you would have to draw it under. But what I love is this is concave up like a cup. This could hold water, this curve. And this is concave down like a frown. So I love this way to think of it better, like a frowny face. But curves aren't always this simple to where they're only concave up or concave down. You might have a curve like this one here, and it's got different types of concavity in it. Maybe from here to here, it's concave down like a frown. And then from here to here, we're concave up like a cup. So where the concavity changes in a graph like this, where we stopped being concave down and we began to be concave up, this point right here where the concavity changes is called a point of inflection. So the point of inflection is the point where concavity changes. So there are a lot of similarities in this section and in section 3.3, where we were doing increasing and decreasing intervals. So first off, we have a test for concavity. And it is if the second derivative of x is greater than 0 for all x in the interval. Then the graph is concave upward. On the interval. So that's nice. I really love that second derivative is greater than 0. That means it's positive. And we are concave up, which sounds like a positive thing. So I love that there's that similarity. And the second one is just the opposite. If the second derivative of x is less than 0, I'm not going to write all this stuff. Then the graph is concave downward. So we love that. Similarity to less than 0 is negative, and we're going downward. So that's great. And then we're ready to do an example where we test for concavity. And like I said, you're going to see lots of similarities for section 3.3. Determine the open intervals on which the graph is concave, up or down. And f of x is 6 over x squared plus 3. So when we are talking about concavity, we have to keep glued in our minds that concavity goes with the second derivative. So the function gives us absolute extrema. The first derivative gives us increasing and decreasing, where we can find a relative min and a relative max. The second derivative gives us concave up and concave down, where we can find points of inflection. So I kind of would like to rewrite this way so I could use the chain rule, but quotient rule isn't bad. But I think I'll just group this denominator, and it's to the first power, and then I'll bring it to the numerator and make it to the -1 power. That makes it a little nicer, I think, to do my derivative. So chain rule says the -1 comes down and multiplies with the 6 times the inside part to the 1 less times the derivative of the inside part. And then we want to clean that up a little bit and call that -12x. But I'm not going to switch this to the denominator because I need to do the second derivative. So I just cleaned it up a little bit, put it sort of in the same form that we rewrote the function to. And now we'll be able to do the second derivative. You do have to pause and look here, though, because this has an x with it. So I can't just do chain rule on it. I have to do the product rule with chain rule inside of it. Otherwise, you rewrite it and move that to the denominator, and then you do the quotient rule with chain rule. So I'm going to do the product rule with chain rule. So second derivative is first times the derivative of second, and we have to do the chain rule on this second term, to the 1 last times the derivative of the inside, plus the second times the derivative of our first. Oh my, we need to clean this up a little bit. So -12 times -2 is 24 times +2 is 48. The x times the x is x squared, and we're going to bump that x squared plus 3 to the third to the denominator. And over here, we're going to have -12 over x squared plus 3 to the second. Just like with section 3.3, we needed a solid fraction so that we could set the numerator equal to 0 and the denominator equal to 0 to find those critical numbers. We need that solid fraction here too. You can butterfly, or I'm super tempted to just multiply this second one by another x squared plus 3 to get x squared plus 3 to the third for both of these. And then we have to be fair and do this one also. So I'm running out of room a little bit. Sorry about that. So let's continue our derivative up here. That gives us 48x squared. And let's distribute with the -12 here. So -12x squared minus 36. All over our denominator, x squared plus 3 cubed. So that gives us 36x squared when we combine like terms, minus 36 over x squared plus 3 cubed. Now, we've got our second derivative, and we've got it as a solid fraction. So we will set the numerator equal to 0, and the denominator equal to 0. And this will help us to find our possible points of inflection. Here, since we don't have all three pieces of the quadratic, we can just add the 36, solve for x, divide by 36, and take our square root. And here we're going to cube root both sides. We're going to subtract the 3. And then do the square root, and that's imaginary, so it's not real. So we won't get a point of inflection from it. So our possible points of inflection are plus and minus 1. To determine if they are points of inflection, we put them on the number line. So similar to 3, 3, we space them out between negative infinity and positive infinity in the order that they would come. And we draw down from those possible points of inflection, which separates us into some intervals, negative 1 to 1 and 1 to infinity. And we choose a nice number in that interval to test, like negative 2, but we test it in the second derivative. And this one will test 0, and this one will test positive 2. So now we have this second derivative here, and we're going to plug in these test values that we just chose, and we need to know if it's positive or negative. That's all. We don't need to know the exact values, just whether it's positive or negative. So we can use our calculators or whatever we'd like. I'm just going to cheat a little bit and say this is positive. That means we're concave up here. 0 gives us negative. That means we're concave down here. And 2 gives us positive, which means we're concave up. And so since concavity did change from concave up to concave down, this is a point of inflection. And since at 1 concavity did change, it's also a point of inflection. So normally it feels like it does alternate, concave up, concave down, concave up, but it doesn't always. Sometimes it'll be concave up, then concave down. So if it did not change, if this was actually concave up and concave up, then this negative 1 would not have been a point of inflection because concavity didn't change. All right. That gives you some stuff to think about. The only problems I want you to try for me are on page 192. Let's try number 3 and number 7. If you'll try those by following the steps that I just did with you, then I think that would be a good start for us.